Now let us discuss population inversion in relation to number of participating energy levels in the process of lasing. In the example shown in the earlier slides, we considered, for the sake of simplicity, the process of creation of population inversion between the ground and the excited level without involving any other energy. We always have used two levels. I shall now explain to you the insurmountable hurdles posed by a two-level system toward achieving population inversion, and in turn its impracticality to allow amplification of light. In a real laser, the involvement of at least one more level allows the creation of population inversion and in turn lasing. I shall also explain to you of overcoming the challenges of a two-level system by going for a three-level. I shall also try to tell you how a four-level laser system is regarded as an ideal laser, because three-level schemes also have some disadvantages. A four-level laser actually removes the challenges of three-level. Optical pumping, capable of providing resonant photons prerequisite for the onset of absorption and stimulated emission processes, will be made use of as we examine the pros and cons of lasing involving 2, 3, and 4 energy levels. Let us consider the case of two-level system. We begin by considering two atomic energy levels, one ground that we denote by energy E0, and the other the higher energy state that we denote by energy E1. And the population is first distributed following Boltzmann distribution, and therefore the majority of the atoms, let us consider atoms, are in the ground state, electronic state, and hardly there are any atoms in the excited state. The medium is now shown by a beam of light comprising of resonant photons that far exceeds the total number of species. We have used the term far exceeds because that helps in understanding explanation of this process. So now then what will happen? This lower level is populated much more than the upper level. So these photons, incident photons, will largely interact with this species present in the lower. And because these are resonant photons, photons' energy, you will see, matches with the energy difference levels. So these atoms will start absorbing photons and climb up to the excited state. So as it happens, this beam loses energy, loses photons to this medium, because the atoms are absorbing photons and climbing up the energy, climbing up, making transition to the upper material. As this is happening, so the beam is also losing photons, those photons which have been absorbed. So this is reflected in this picture by a lesser, smaller width of this beam compared to this. This means its intensity is more. That means initially this beam is losing photons to this medium. Now you see what happens. So some population from the ground state has now appeared in the higher energy state, which we denote by red atoms. They're hot. So what will happen now? Some of the photons will now start interacting with the atoms present in the excited state. So earlier, most of the interactions were occurring with the atoms present in the ground state. Now, because the higher energy states also getting populated, there will be increasing number of interactions with the atoms excited to the higher energy state. Now, what happens? You already know when they interact with the excited state atom, they will come down to the ground state and will add photons to this incident. So now the intensity of this photon will increase because true, photons are being absorbed from here, but this absorption is now less than what was happening before, because earlier there were mostly these atoms were present. Now this atom has become less, and their number is rising. So the absorption will become less now, and there will be some emissions also which will add photons to this. So it is reflected by a corresponding increase in the width of this transmitted beam. That means the beam is now losing less amount of photon to this medium. It is still losing because its intensity is still less, but not as much as it was started in the beginning. It is a dynamic process. It is happening. I have just captured some states in between. Now, as it is happening, more and more atoms are jumping up into the excited state. And eventually, a state will be realized when the excited state and the ground state both have equal number of species. You see, in this scenario, you have 6 red atoms, 6 green atoms. What will happen now? You already know. Now this beam of light will interact with the ground state, the excited state, with equal probability. Therefore, this beam will pass through this medium unhindered. So when this happens, will there be, can you create population inversion? No. A situation would therefore inevitably emerge where the excited state population equals that at the ground state, and it will remain forever, remain so forever. Beyond this point, the incident beam of photons will continue to interact evenly with the atoms in the 2 states, equal probability, and thus would emerge through the medium unhindered, leading inescapably to a stalemate-like situation. As the number of atoms in the ground and excited states are same, the probability of interaction of the incident beam of light with either of the energy states becomes equal. At any instant, if one photon from the incident beam is lost due to absorption, the process of stimulated emission adds the photon to it at that instant. Undoubtedly, therefore, it would be impossible to create population inversion in a 2-level system. A laser thus can never be conceptualized on a 2-level scale, let alone its operation. This 2-level impasse can be readily overcome by involving the service of a 3rd energy level in the process of lasing. The 3rd energy level, called the pump level, which we denote by G2, is usually located slightly above the upper energy level, which of course is denoted by E equal to 1. This is in the 2 level, this is the upper energy level, this is the upper energy level, this is the lower one. Now in the 3-level scheme, we have added another energy level to it, which we call pump level, and which is located slightly above this level. So it looks like this. And as before, we now describe the working of such a 3-level laser based on such a 3-level scheme. So your ground level to begin with has the maximum population. So it is basically our source level. And let us assume the upper level and the pump level are practically empty. Now you shine this medium by a beam of light which is resonant to this transition, ground to pump, not the upper level. So once again, then you will start transferring population from the ground level to the upper level. Now you have chosen these levels in such a way that this level is very efficiently coupled to this level. That means the moment you transfer population from the ground level to pump level, it immediately appears in the upper level. It relaxes through non-radiative process. Relaxation doesn't occur through emission of photons. It is a non-radiative process. This emission occurs, this relaxation occurs through thermal process. The energy is actually realized transitionally. It increases the temperature. I will not go into much detail, but accept it that this level, pump level, we call it pump level, and the upper laser level are very effectively coupled. It relaxes very fast to the upper level. So that means what is happening? These atoms which you have transferred to the upper level, pump level, it immediately arrives at the upper level. So the chance that stimulated emission will again bring it back to the ground level doesn't exist here, because the atom immediately comes here. It doesn't allow this pumping photons to interact with it, and by stimulated emission sends it back to the lower level. That's what was happening in case of a 2-level system. And these photons cannot interact with the atoms which are in the upper level because their energy doesn't match with this. Their energy that these atoms carry, the excitation energy, is less than this by this much. Some of the energy has been dissipated as heat. So these photons cannot stimulate the atoms here. So once they arrive here, they stay here. And actually, you choose such a medium which not only allows you this kind of energy level, but also this level is a metastable. A metastable level is one where population can reside for a longer duration. You see, this comes from some spectroscopic rule. Some of the levels, not all levels relax at the same rate. Some relaxes faster, optically of course, some relaxes slower. So this follows from some set of spectroscopic rules and guidelines, which of course is beyond the scope of this course. So accept that these two levels are very strongly coupled, and then this level, which is the upper laser level, is a metastable state. That means you can accumulate number of atoms here for a longer time. So basically you are transferring population from the ground state to the upper laser level via the pump. You are taking help of the pump level because you want to decouple this from this level. Otherwise, this photon will stimulate them back to the ground state, as you saw was happening in case of the 2-level system. Because these photons would not only absorb this, photons not only would be absorbed by these atoms and climb up, they would also at the same time bring them back. So finally, you will have such a situation where both the levels have attained same population, and from there it is that's where it will stay. You cannot change this condition. So here you are taking advantage of this third level. So upper level is usually metastable state, as I said. Therefore, the atoms reside here for a relatively longer period and do not immediately spontaneously decay back to the ground state. This allows gradual accumulation of population at the upper level, giving rise to the prospect of inverting population between the ground state, which is the lower level, and this is the upper level. So you have created a population inversion, as you can see. It's just schematic where lower level 5, the upper level 6. However, there are some disadvantages of inherent disadvantages of a 3-level scheme. Because you see, because here the lower level is also your source level, because all the population is initially residing in this level. Therefore, to create population inversion, you will have to, to create population inversion, you will have to take more than half of this into this, and of course via the pump level. So that means you have to consume lot of pump photons to achieve this inversion. And I am only showing here just 10, 11 atoms, but in reality, these numbers will be billions and billions, and you have to just calculate how many. So, you see, you have a 3-level system. This is my source level, which is also the lower level. And this is my pump level. And this is the upper level. Now, source level will have part CC, innumerable number of atoms. Innumerable. You know Avogadro's number, you can calculate depending on that. So if you have to transfer, let us consider we have 10,000, we have to transfer 10,000 atoms. We have to create population inversion. So if you have to create population inversion between this and this, out of 10,000, you have to transfer at least 5,001 atom here. So that here there are 4,999 atoms. And this will be via this. So for transferring each atom, you need this much energy. You have to spend this much energy. Now the funny fact is that you have created, even after transferring so many atoms, there is a population inversion of just one atom. So if there is one Lessing transition, this is going to be 5,000 and this is going to be 5,000. Your population has been killed, inversion has been killed. So to maintain population inversion, you have to pump it very hard and continuously. That is why the operating efficiency of such 3-level lasers is pretty low. And they are not very attractive system either. Maintaining population inversion with a 3-level laser is indeed a very expensive affair. And quite predictability, this class of lasers suffers from rather poor energy extraction efficiency. This is reflected in the fact that a significant fraction of photons, the pumping beam of light is consumed in initiating and sustaining lasing here. Incidentally, the first laser that Neyman operated in 1960 was based on such a three-level scheme. So the problem of this three-level system can be overcome in going for a four-level system. This, what you basically do here, you bring another level. You decouple actually the lower laser level and the source level. You add another level, which you call the lower level, and you place it sufficiently away above the source level to ensure that the population, thermal population of this level is very small. This follows from Boltzmann distribution. You see, if these are two levels, this is my upper level and this is the lower level, then N2 is equal to N1 e to the power, this is the energy delta E to the power minus delta E KT. So N2 equal to N1 by e to the power delta E KT. So we want to basically make N2 smaller, as small as possible, to increase this gap. If we increase this gap, then this becomes more, denominator becomes more. If the denominator is more, then N2 reduces. So you increase the gap so much so that thermal population of this level is almost, there is hardly any thermal population. So to begin with, your lower laser level is empty. While in a three-level system, the lower level actually contained initially all the population, and you are actually transferring population from the lower level to the upper level, of course, at the pump level. So you understand the advantage that this gives. Now you have the pump level, of course, because you are decoupling the upper laser level from the pump level to remove the challenges of two-level scheme. So now you again pump this laser by beam of light, which is resonant to this transition. Ground level to, this is my pump level here. So you transfer population from ground level to pump level, and which immediately arrives here. They are very strongly coupled, as in the previous case for three-level system. So now you see, even if you have transferred just one atom from the ground to the upper level, via of course the pump level, you have achieved population inversion because this level is practically empty. Compare it with the three-level case. You have to transfer so many just to get some marginal population inversion, and that would be killed just with the onset of lasing. And this, and you again use such energy levels where this level and this level, like the pump level and the upper laser level, is also strongly coupled. This is indicated by this broken line. So the moment this, as an upshot of lasing, this atom, after lasing, it will come to the ground state and it immediately appears here. So that the atoms always participate in the process of lasing. The rapid relaxation of the lower level population to the ground level ensures that the population arriving here as an upshot of lasing are immediately drained to the ground, and in turn their non-stop participation in the process of lasing is ensured. The inherent ability of the four-level scheme to preserve population inversion with relative ease makes this class of laser ideal. most ideal laser system. It is not surprising that they intrinsically offer higher extraction efficiency. Today, most of the lasers that operate are on a 4-level energy scheme, and we will learn more about them as we move along this course and deal with specific laser systems. Let me end here today.